Exercise 6.15. Lines L1 and L2 are given by the equations L1 r equals 9, negative 12, 12 plus t times 6, 1, negative 6, and L2 r equals negative 5, 7, negative 8 plus u times 4, 3, 3. Show that L1 and L2 do not intercept. Find an equation for the common perpendicular to both L1 and L2, and find the shortest distance between L1 and L2. No problem. Let's do the first part. If they did intercept, we would have 9 plus 6t is equal to negative 5 plus 4u. We would have negative 12 plus t is equal to 7 plus 3u. And we would have 12 minus 6t is equal to negative 8 plus 3u for some value of t and u. So we have to show that there are no such t and u to make that true, just because of the convenience of negative 6t and positive 6t. I'm going to go 1 plus 3, and so that'll give the equation, so 9 plus 12 is 21. And then the 6t and the negative 6t cancel out, and that's equal to negative 13 plus 7u. And so we have that u is equal to 34 divided by 7. Substituting that into equation 2, we have t is equal to 12 plus 7 makes 19 plus 3 times 34 over 7. And that is equal to 235 divided by 7. Alright, so we have proven that if there were such u and t, there would have to be 34 over 7 and 235 over 7. And they have to satisfy all three equations. Let's see if they satisfy the first one. So we have 9 plus 6 times 235 divided by 7 is supposed to equal negative 5 plus 4 times 34 over 7. Which is clearly not true. Therefore, the equations are inconsistent. And so L1 and L2 do not intercept. Okay, moving on to the more interesting stuff. Find an equation for the common perpendicular to both L1 and L2. Okay, just giving myself a bit of space here. So let's say that this one is L1, and then we have L2, I don't know, maybe it looks something like this. Okay, and we're looking for the common perpendicular of L1 and L2. So we have this line that goes through and intercepts each of the lines L1 and L2, while simultaneously being perpendicular to both of them. Now we have a direction vector for L1, that is 6, 1, negative 6. And we have a direction vector for L2, which is 4, 3, 3. So we know that this line is parallel to the normal vector n, which is the cross product of these two vectors. So n is equal to 4, 3, 3 crossed with 6, 1, negative 6. Alright, so then 3 times negative 6 is negative 18, minus 3 is negative 21. And then deleting the second row, we get 6 times 3 is 18 minus negative 24. So that would be 42. And then finally, 4 times 1 is 4, minus 18 would be negative 14. And if you want just to make calculations slightly easier, you can divide it by 7 and get another normal vector. So negative 3 and 6 and negative 2. Right, so that's the normal vector we'll use. Okay, and we also know that there's a point, let's call it B here, and a point A here on L1. And using the information that we have now, we can go ahead and find these points A and B. So we know that OA is equal to, let's say, 9, negative 12, 12 plus A times 6, 1, 6. Sorry, 6, 1, negative 6. And we know that OB is equal to negative 5, 7, negative 8 plus B times 4, 3, 3. And we also know that OB is equal to OA plus K times plus AB, but we also know that AB is equal to K times our vector N1. Okay, so subbing everything in, we've got negative 5, 7, negative 8 plus B times 4, 3, 3. So that's our vector OB. That's equal to OA, so 9, negative 12, 12 plus A times 6, 1, negative 6 plus AB, which is equal to K times N1, so plus K times negative 3, 6, negative 2. And these are the unknowns, the B, the A, and the K. And so we have 3 linear equations with 3 unknowns. Let's transfer this 9, negative 12, 12 vector over here first by subtracting it from both sides. So we get negative 5 minus 9 is negative 14. 7 minus negative 12 is positive 19. And negative 8 minus 12 is negative 20. Equals. And then let's write everything as a matrix over here. So 6, 1, negative 6. And then negative 3, 6, negative 2. And then we're transferring this vector to the other side, which means we're subtracting it from both sides, which means we're going to have negative 4, negative 3, and negative 3. And then this is times the vector A, K, B. And so this matrix equation is equivalent to this sum of vectors, this sum of vectors equation. You can multiply everything out if you don't believe me. And now it's pretty easy. You can solve this on the calculator, or you can do it by hand, or however you want to do it. But you get that A is equal to 1, K is equal to 4, and B is equal to 2. By the way, if you are doing it on the calculator, you can go to Menu, and then Equations, and then Simultaneous. And then the number of unknowns is 3 unknowns. Alright, anyway, now that we know little a, little b, and k, that allows us to find the vector, for example, OA and OB. So let's go ahead and find those two. So OA is equal to 9, negative 12, 12 plus little a, which is 1, times the vector 6, 1, negative 6. So 9 and 6 makes 15, negative 12 plus 1 makes negative 11, and 12 plus negative 6 makes 6. So that's our vector OA. OB is negative 5, 7, negative 8, plus little b, which was 2, times 4, 3, 3. Okay, so negative 5 plus 8 is 3, 7 plus 6 is 13, and negative 8 plus 6 is negative 2. Oh, and we also know the vector AB, which is equal to k times n1, is actually equal to, so k is 4, and the vector n1 we had was negative 3, 6, negative 2. So that is negative 12, 24, and negative 8. And now we're ready to answer the question, which was to find an equation for the common perpendicular to L1 and L2. Now that is, of course, the equation of the line that goes through the points A and B that we found. So we just need the equation of the line through A and B, and we know that, for example, one possible vector equation is R of t is equal to OA plus t times AB. So that would be, well, OA is 15 and negative 11, 6, plus t times AB we found was negative 12, 24, negative 8. So that's one possible vector equation for the common perpendicular of the lines L1 and L2. And lastly, it says find the shortest distance between L1 and L2. That's just the length of AB. So all we need to do is find the length of AB, so distance between L1 and L2 is equal to the length of the vector AB, which is equal to, so AB is equal to this vector here, so it's equal to the square root of 12 squared plus 24 squared plus 8 squared, and that's equal to 28. And that's all for this problem.